Okay, let's start. Today we are very happy to have Aditya to give a talk on some new type of algorithm for reinforcement learning. And Aditya is a PhD candidate at the University of Florida. He's currently an intern at Tencent's AI lab. So we grab him for a few hours to give a talk. And yeah, he has also visited recently the Simons Institute at Berkeley. Okay.
Okay. Thank you, Len. Thank you, Len, and thank you all for coming here. I'm very happy and excited to be here. So today I'll be talking about stochastic approximation and reinforcement learning algorithms, which is a joint work with my advisor Sean Mine at University of Florida and also Anna Busic at India. So this is the, sorry?
What's that logo?
This one? Yeah. It's Zapdos. It's a Pokemon. It's kind of like, you'll probably see the connection. Anyway, this is the basic overview of the talk. So first I'll be introducing what stochastic approximation is, very briefly. And I'll also be talking about how to speeden it up. I'll also be introducing some of our new work on optimal momentum stochastic approximation. And then I'll be connecting all of these algorithms to reinforcement learning problems, and then also be talking about our work on Zap Q-learning. And I'll be concluding with some future work. Okay. So what is stochastic approximation? The goal here is pretty simple. You have a parameterized family of functions f bar, which is actually an expectation of some function f of theta comma w. Here, the w is a random variable, and this expectation is with respect to the distribution of this random variable. And you want to find the parameter vector theta star so that f bar of theta star is equal to 0. And this can be like any function f bar. It can come up in optimization or anything like that.
So here, w is a random variable?
Yes, w is a random variable, okay. And theta is the parameter vector.
Okay. That's the opposite.
Oh, yeah, the little w. Yeah. Yeah, this is linear process, and it comes from the control whatever community, I guess. Anyway, why is this hard? First of all, the function f or the distribution of this random variable w may not be known. Even if everything is known, calculating this expectation, calculating the integral might be like very hard. And for root finding problems, you need to find this integral for multiple values of theta, which can be very expensive. And finally, the recursive algorithms that we come up with are often slow, and their variance may be infinite. So I'll be talking about what exactly this means and how this is true in like the Q-learning algorithm, which is a special case of stochastic approximation. Okay? And we showed this in our recent paper like last year. So how do we solve this problem here? So the classical algorithm of Robbins and Monroe is like given by this recursive equation here. So you evaluate this noisy function f of theta n at wn plus 1, and then you update the current estimate theta n plus 1 like this. So this alpha n plus 1 is a positive step size sequence. It has to satisfy certain properties. So here we are looking at a decreasing step size scenario. I think the theory can be extended to constant step size too. But throughout this talk, I'll be talking about decreasing step size, and we'll usually take alpha n is equal to 1 over n, which satisfies these two properties. Okay. We can rewrite this recursion as like this recursion here. So basically, I've replaced this noisy function with the mean plus a zero mean sequence. So this is the error term. And what this looks like is basically a noisy discretization of the deterministic ODE, which is basically the motivation for Robbins and Monroe algorithm. And under stability, assumptions on the stability of this ODE, and a lot more assumptions on what kind of noise you're dealing with, and boundedness of parameter sequence, other things, you can show that this parameter recursion, like theta n plus 1, will converge to theta star. And there are a bunch of assumptions. And you can look at Borker's stochastic approximation book for more details.
Are you only assuming you can sample wn plus 1s from the distribution?
No. So, I mean, we don't need it in any of my work. So all we have is f of theta n comma wn plus 1. Yes, so the common notation is fn plus 1 of theta n in the optimization literature. So that is also equivalent. So yeah, so I won't be talking a lot about the convergence itself. So what I'm really interested in is like how to improve the rate of convergence, assuming that there is an algorithm that converges, how to actually improve the rate of convergence. Okay. So let's look at a very simple example to start things off, which is Monte Carlo estimation. Let's say you have a random variable w and a function of the random variable c of w, and what you're interested in is finding this expectation, okay? And it is given by this integral here, assuming that it has a density given by rho, okay? The stochastic approximation interpretation of this problem is you want to find the theta star so that this is equal to 0, right? So if you find theta star of this equal to 0, then theta star is equal to expected value of c of w. And there's another like classical way of solving this problem, which is basically the Monte Carlo estimate of the sample average, right? So, so what this is showing is that you can write this Monte Carlo average in a recursive fashion, and what it turns out to be is actually a stochastic approximation recursion with a very specialized step size alpha n plus 1 given by 1 of n plus 1. So earlier I told I'll be choosing alpha n is equal to 1 by n, that's typical. But here it's very special because like I could have chosen any other step size which satisfies these two conditions and still the algorithm will converge. So theta, you can show that theta n will converge to theta star where theta star is expectation of this. But there's only one step size, alpha n is equal to 1 over n, that will result in this Monte Carlo recursion. And that is the statistically the optimal thing to do. So we want to kind of like generalize this and show how to kind of choose this step size sequence so that like it's statistically the best thing to do. Okay?
So in this case, is 1 over n plus 1?
Yes, alpha n plus 1 is 1 over n plus 1. So just by looking at this recursion here, I divide through it by n plus 1, I get like alpha n plus 1 over n. Yeah. So alpha n is 1 over n.
I mean, you have to be, I know it probably doesn't maybe matter in the types of things where you're talking, but you have to be careful in making the claim that that is the optimal thing to do, even because it depends. Like if W were a high dimensional quantity and you start talking about the optimality of sample mean, you'll get into shrinkage issues.
So I totally agree. So what I mean by optimal thing to do is like in a very specific sense. Right. So I'm talking about the central limit theorem variance. So it has the optimal variance. So that's, I'll talk about this in a couple of slides. Okay. So how do you fasten stochastic approximation? Okay. So there are two standard, like I guess there are many more, but oh yeah, this is just a slide. So this is infinite variance stochastic approximation algorithm, and this is a finite variance stochastic approximation algorithm, and this is the optimal algorithm. So if we don't know where theta star is, if you look at these three algorithms, so this looks very nice, right? But it has infinite variance, so it's going to take forever to actually read theta star. So this is like one of the slides that Sean actually often uses to show that just because you get a curve like this does not mean that it is like good. So yeah, so and green is like much better than this red curve. So even though it has like a lot of fluctuation. So there are two standard like criteria for deciding the performance of stochastic approximation algorithms. So one is like looking at the finite n bounds. So you look at the error sequence defined by the parameter estimated time step n, difference between that and theta star, and then you want to bound the norm of this error, and you want to say the probability with which that is greater or equal to epsilon is less than or equal to something, and you want that to go to 0 exponentially fast. So there's another like probably not so popular way of looking at the performance of stochastic approximation algorithms, and that is the asymptotic variance. And so what we care about here is this limit over here. So this is basically the central limit theorem variance. And assuming that this limit is finite, then what that says is that square root of n times the error sequence is distributed according to Gaussian with mean 0 and variance of this sigma, which is the limit. And that tells you that as n goes for large n, and that tells you that the asymptotic rate is like 1 over square root of n with the constant like sigma. Okay, so this will be the focus of the talk. So we'll be talking about how to optimize this asymptotic variance and how to get like good algorithms that often like achieve this variance.
What kind of connection between these two parts, two approaches?
So
my question is, are they just more or less equivalent?
No, I don't think they're equivalent. But I think like so. I think you can get this kind of a bound asymptotically using this. So, but you can't get like this. I mean, what I'm trying to say is like you can get like this kind of bound from this, but I don't think it goes the other way around. This is all asymptotic.
If you have the asymptotic covariance, you know that it's also in that exponential form asymptotically, where I epsilon n would be given by the CLT.
Yeah, exactly. Yeah, so
by the corresponding Gaussian.
okay. Okay. So how do we like try to estimate this? How do we find, given an algorithm like this, how do we find what the asymptotic variance is? So let's look at the original recursion. So given this recursion, you can like basically, given this formula here, n times expectation of theta tilde and transpose, you can actually obtain a recursion for the sigma n itself, and it is given by this recursion here. So I've used a bunch of like Taylor series arguments and like some ignoring some terms. So there's an approximation here. You can show that you obtain a stochastic approximation for the sigma n itself. And it is given by this recursion here, where A is the linearization of this function f bar at theta star, and sigma delta is the covariance of this zero mean noise sequence delta n plus 1. Okay. And looking at this recursion, what this says is that if the eigenvalues of this matrix A plus half I are all stable, that means like if all the eigenvalues of this A matrix are less than minus half, then this recursion converges. And its limit is actually given by this Lyapunov equation here, basically the terms inside over here. And if any of the eigenvalues of this A matrix are actually greater than or equal to minus half, then this recursion is unstable, and then this will diverge. And that.
Remind me what delta is?
So delta is the mean minus the fn plus 1. So basically the zero mean. Yeah, in simple example.
It's the mean minus theta or?
F of theta n comma wn plus 1. So I think it's the mean minus this. Oh, sorry. It's in the first slide, I think. Oh, it's here. So delta n plus 1 is the mean minus this fn plus 1.
I see. It's just the unbiased.
Unbiased zero mean. It's like martingale difference sequence. So and this is the sigma delta is the variance of that. And so yeah, if the eigenvalues of this A matrix are at least some of them are greater than or equal to minus half, then this diverges. And what this is saying is the asymptotic variance is infinity, and it's also saying that the convergence rate, asymptotic convergence rate is slower than 1 over square root of n. Okay, which is not good. Like it's not optimal. So now that we know how to calculate the asymptotic variance given a stochastic approximation algorithm.
In this one, what step size you use for this?
1 over n.
1 over n. Okay.
Yes. Alpha n is 1 over n. So exactly. So specifically for 1 over n, this is what you get. Okay.
For like others, like slightly like n to the some power larger than
less than 1.
Less than 1.
Then you can show that the variance is infinity.
Variance is infinity.
Yes. So, but it has like good transients. So there's a trade-off there. So you can use 1 over n power 0.85 or something like that. So you get very good transients closer to the optimal, but it does not have asymptotic rate of like 1 over square root of n. In fact, if you use step size 1 over n power say 0.85 or whatever, then you can show that the convergence rate is like 1 over n power 0.85 by 2. So it's like slower than 1 over square root of n, but it's yeah. But in Polyak'smomentum averaging, what they do is they use that kind of higher steps in the beginning, and then they average it out to get optimal asymptotic variance. So I don't know, I might talk about that very briefly. So now that we know how to obtain the asymptotic variance given algorithm, so let's introduce a matrix gain Gn plus 1. So Gn plus 1 is a d by d matrix. So I should have mentioned theta is an Rd, and this function also maps from Rd to Rd. F bar maps from Rd to Rd. So Gn plus 1 is a d by d matrix. Assume that this Gn plus 1 will converge to some matrix G. And then we can obtain a recursion for this error sequence, like subtracting of theta star from both the sides. And then you can obtain like exactly what I said earlier, but for this new algorithm here, and show that if the eigenvalues of this matrix GA this time are greater than or equal to minus half, then you can show that this corresponding asymptotic variance is infinity. And if all the eigenvalues of this matrix GA are less than minus half for all, if all the eigenvalues of matrix GA are less than minus half, then you can show that the variance solves this new Lyapunov equation over here. Okay, and it actually tells us more. It tells that if you use G is equal to G star, which is basically minus A inverse, this recursion here, it looks like Monte Carlo. If you just take this minus A inverse here, you have minus theta tilde n minus A inverse of delta n plus 1. So basically averaging out this noise in some way. And
assuming that A is like a square matrix.
A is a square matrix, yes. So like I said, F is F bar maps from D to RD to RD. Yeah, and this algorithm also resembles the Newton-Raphson algorithm, the classical, the root finding Newton-Raphson algorithm, and it is statistically the optimal thing to do in the sense that the asymptotic variance is given by A inverse sigma delta A inverse transpose, and if you use any other matrix gain G, it's not going to be optimal. That means the sigma star minus sigma G is going to be negative semi-definite. Okay. Yeah. So. And Polyak'smomentum averaging, you can show that wherein like you use a higher step size in the first loop and then you average out the parameter sequence in the second loop. You can show that even that has optimal asymptotic variance, but it does not have the transient behavior as this Newton-Raphson algorithm wherein you use this minus A. Yeah. Now, any questions? Yeah.
This one, alpha n plus 1 is not set to 1 over n.
It's still 1 over n. Alpha n is 1 over n throughout the talk. Yeah, almost. So you use alpha n is like 1 over n and G is equal to minus A inverse, and then
and the other question here was, so A is unknowable, right?
Yes.
You're doing F bar of theta star,
yes,
essentially. So what's the practical way to set G?
Yeah, I think we'll talk about it in two slides. So let's look at a very simple example. Again, the Monte Carlo recursion. Again, the goal is to find this expected value of C of W. Now here I'm letting alpha n to be G over n for any G greater than 0. What we wish to see is like how the algorithm performance varies depending on the choice of G. Does this asymptotic variance actually mean anything? Okay. So again, you're letting this delta n to be the zero mean noise sequence defined to be the noisy function minus the mean. And then you can obtain the recursion for error sequence, like as I did before, just for analysis. Here we let W be a Gaussian with mean 0 and variance 1, and you're interested in estimating the variance. Okay. So I told you that you'll find the Lyapunov equation, right? Like in general, you can't solve the Lyapunov equation to obtain the sigma, but in the scalar case, you can actually obtain the formula for the asymptotic variance, and it is given by this equation here. And by plotting with the varying G, you see that the variance is minimum at the choice of G is equal to 1. This is only for the scalar Monte Carlo mean estimating case. And you see that it blows up as you make G closer to half. And this is exactly the thing I was talking about earlier, that if the eigenvalues are going closer to minus half, then the variance basically blows up. And actually, if you make G too large too, then it's also not good, and the variance blows up like linearly instead of like exponentially if you make it too small. So yeah, my suggestion is use bigger G, it's fine, but make it too small, it's very bad. And if you make G less than half, then the variance is infinity. Okay, so does this mean anything in the performance of algorithms? So here is a simulation of wherein I'm trying to estimate this mean using different stochastic approximation algorithms of different step sizes. So different values of G, 20, 10, 1.5, and 0.1. So these two algorithms have infinite asymptotic variance. And these three have like finite asymptotic variance, but the optimal one is G is equal to 1. And you see that the G is equal to 1 algorithm converges the fastest. The cyan color is the optimal theta star. But other algorithms, the finite variance, they kind of oscillate around the optimal. But the infinite asymptotic variance algorithms, they go, at least the one with the 0.5, it goes very close, but it takes like forever to actually reach theta star.
Are you plotting the averaged one in this graph or not?
So this is a plot of theta n.
No, but so you're not plotting the performance of Polyak'smomentum?
No, I'm not plotting the performance of Polyak'smomentum. I had some slides, I didn't put it here, but Polyak'smomentum averaging is as good as this G is equal to 1 case.
Right. I mean, like, I guess traditionally the main argument has been exactly what you just described, that with 1 over n step size, you better get a constant just right, otherwise you
Yes.
especially on one direction, you'll pay exponentially.
Yeah.
But if you're better off just doing a more conservative step size, like 1 over root n or something, and then do your averaging, and then like you'll never have this sort of exponential blow up.
Yes, but like I said, the Polyak'smomentum averaging, it has optimal asymptotic variance, but the rate of convergence to that asymptotic rate can be like very bad. I'll show in some of my experiments that Newton-Raphson has this special thing that it has optimal asymptotic variance, but it also has like extremely good transients. So that's the difference between like Polyak'smomentum averaging and any of these algorithms. And Polyak'smomentum averaging, I think it's really good for scalar cases, but higher dimensional, I don't think it's good. So this A matrix is like a scalar, then you can do good, but if it is like 100 by 100 dimension thing, I think it has something to do with using constant step size. You want to kind of condition the whole matrix, which can be very hard using a scalar. So
you can have a matrix even
exactly. So
in the averaging case.
So what I'm saying is it won't work very well because you have to. So if the condition number is very bad of the matrix, then that one constant thing, it can't really help too much. Okay. So yeah, back to your question, like how we know what the optimal matrix gain is, how do we estimate it? So in the case of linear examples, like say f bar of theta is a theta minus b, so basically you can do Monte Carlo averaging. So you sample this a case and then you use like sample mean of that to be the matrix gain over here. Again, an plus 1 is a noisy linearizations, and what you get is like basically two parallel stochastic approximation algorithms, one wherein you're estimating the parameter theta and another wherein you're trying to estimate this matrix gain a hat. Okay, so basically this answers the question about how do we know minus a, right? You estimate it on the go. So for those of you who know like this algorithm called least squares temporal difference lambda algorithm, this is basically what it is doing. It does it in one shot. This is a recursive way of doing LSTD lambda, but they had no motivation of reducing the variance or anything like that. But yeah, so this is LSTD lambda. So things are fine if f bar is linear in theta. What do you do if there is nonlinearity in the function f bar, which is the case in, for example, Q-learning? So in this case, what you want is a hat n plus 1 to be the estimate of the mean of a of evaluated at theta n. You don't want the averaging over all the past samples equally, but you want it to be the estimate of the mean evaluated the current parameter estimate theta n. So how we solve this problem is using 2-time scale stochastic approximation algorithm. So what we do is we use a higher step size. So we use different step sizes of alpha n plus 1 and gamma n plus 1. What you want to do is you want this a hat n plus 1 to be a function of theta n and not the previous thetas. Okay, and for that we can use like a higher step size gamma n plus 1 over here and a lower step size alpha for the recursion for the parameter estimation. And like if you satisfy this condition, like gamma n over alpha n going to infinity, as n goes to infinity, then you can show that this a hat n plus 1 actually approximates a of theta n and not the average of all the previous. Yes.
So now you're not gonna set alpha n as 1 over n then?
Alpha n is still 1 over n.
How?
Gamma n plus 1 is like 1 over n. So yeah, alpha n is 1 over n and gamma n is like 1 over n power rho.
Oh, gamma n over alpha n goes to
yes.
Yes. Okay.
Or alpha n or gamma n goes to 0. So if you choose gamma n is equal to 1 over n power rho, with rho being in this whatever, like between 0.5 and 1, then you can show that you get like you get an ODE like this. So
what are the smoothness assumptions on f here? I mean, it seems like you'll at least need 3 derivatives probably. Oh, sorry, 2 here.
No. Yeah, we need f to be Lipschitz, f bar to be Lipschitz, and I think so here.
I think you at least need the derivative to be Lipschitz, right? Because you
a
the
matrix.
derivative.
Yeah, I think so. So the thing is, in Q-learning we didn't have it. We had just a subgradient, and then we still managed to prove it. So I don't think there are general conditions. But if you have something strong like that, then I think we can prove it in general. So, like I said, this algorithm may not necessarily be stable. Like in deterministic, there are no general conditions for convergence of this kind of an algorithm yet. So we have proved it only for the special case of Q-learning, and the general conditions are still open. And if you look at this recursion here, because of this 2 times scale thing, you can actually replace in the ODE A of xt inverse instead of like something like average of A of x for the previous t's. Okay.
So this ODE is holds only for the gamma and
Exactly.
convergence slower.
Faster.
Oh.
Gamma n is bigger than alpha n.
Oh, okay, gamma is bigger.
Yes.
Okay, gamma is
Yeah.
bigger. But that means you want the A convert faster.
Exactly.
Somehow.
Exactly.
No, tracking faster. Okay.
Tracking faster, exactly.
Okay. So if you set gamma n equal to, for example, same as alpha n,
Yes.
you won't get this.
You won't get it.
That's weird.
Yeah. No, it's obvious, right? If you think about this, so A hat n plus 1 is A. So if it's averaging over all previous thetas, so it won't be the current theta n.
Your
So-
thetas are also changing pretty slowly. You're using 1 over n steps.
Exactly.
So it's
So-
not obvious that it should not work either.
Yeah. So it's a
So the question is, if you set gamma n and alpha in the same order, so what would it, if it's corresponding to anything, or maybe it's obvious and unstable?
So I think if you put in more assumptions, assuming the parameter sequence converges or something like that, then I think you can show that it's still stable. But in general, I don't think you can say anything. So you need a lot more assumptions to actually say that. So the thing is, if theta n like goes closer to theta star or something like that, you can, if you want to analyze it locally or something like that, then you can show that A hat n plus 1 for large n actually approximate A of theta n. So then I think we can probably say something. But in general, it's very difficult.
But even under the gamma n over alpha n going to infinity condition, we don't know whether it generally converges,
No,
right? That's
no.
what you...
Exactly. So even in general, it's very difficult to show this. Yeah.
You said something about subgradient earlier.
Yes.
What are you assuming? So you are assuming convexity or something? Of,
No. So when I say
do you
sub,
know how to define subdifferentials properly for convex functions?
so I'm defining the subgradient, the matrix A for f bar. So meaning, and specifically for Q function, I'll show you what it is. So it's not in general at all here. So yeah, before I talk about reinforcement learning algorithms, like wherein I'll be applying these techniques to obtain the Q-learning, optimal variance Q-learning algorithms, I want to briefly talk about momentum-based stochastic approximation. So this is like kind of my favorite part of the slides, which is very new. And so this is the Zap is basically the Newton-Raphson algorithm, and this is the new like momentum-based algorithm, and you see that it basically couples. So this has a when we wrote this paper on Zap SNR, which I just told, there was a lot of feedback saying that you have a matrix inverse, which can be very computationally expensive. So one of the things we wanted to do is like try to somehow remove that, and that's where like we kind of came up with this momentum-based methods and showed that actually you can get the same asymptotic rates as this is what I'll be talking about. Okay. So let's recall. So here the notation becomes big. So I'm using fn plus 1 of theta to be f of theta comma wn plus 1, and we'll denote delta theta n to be the difference sequence theta n minus 1. Okay. This is the matrix gain stochastic approximation we have already spoken about, just written in a different form. So this is the heavy ball stochastic approximation of Polyak. So basically, there's this additional term where m is a scalar, following this work by Polyak. And what we want to do is like we want to look at an algorithm that looks like this. Instead of the scalar m, we're introducing a matrix sequence mn plus 1, and we're also introducing gn plus 1 over here just to make it more general. So you have a matrix gain multiplying fn plus 1, and you have a matrix multiplying this previous difference sequence, the momentum term. Okay. So the question is, how do we optimize both these matrices mn plus 1 and gn plus 1? So again, rewriting this heavy ball stochastic approximation algorithm, it looks like this. Let's assume for heuristic purposes, let's say that this delta theta n goes to 0 much faster than theta n goes to theta star. Okay. in this case, we can replace this delta theta n with delta theta n plus 1. Let's say it's an approximation. And then you can like take this delta theta n plus.
Delta theta n the same as theta n minus theta star?
No, delta theta n is theta n minus theta n minus 1. The difference between, yeah. Theta tilde n is theta n minus theta star, just clarifying. It's a momentum term. So you can put this, whatever, like this term on the left hand side and you can take the inverse, and this is what the algorithm looks like. And let's try putting like mn plus 1 is equal to I plus gn plus 1 times a hat n plus 1. Okay. In this case, what happens is like this algorithm, this heavy ball stochastic approximation algorithm actually looks like the SNR algorithm, and we didn't invert any matrices here. So again, all this is very heuristic, but we have some rigorous arguments showing that this is actually fine. So basically, what I'm trying to say here is if you have a stochastic approximation recursion like this, if you choose mn plus 1 to be I plus gn plus 1 a hat n plus 1, this is the momentum term, then we get SNR kind of a recursion. Okay. Let's collect all the algorithms together here. This is what the stochastic Newton-Raphson algorithm looks like. I'll let gn to be equal to zeta I for simplicity. In this case, this is what we call the PolSA algorithm, basically the momentum stochastic approximation algorithm with step size with the momentum being equal to this is given by this recursion here. Okay, and this is what the Nesterov's stochastic approximation algorithm looks like. This is basically applying Nesterov's accelerated momentum method to finding a root finding problem. Let's say just writing out the recursion, and if you look at a linear case where fn plus 1 of theta n is linear in theta, this is what it looks like. Basically looks like the noisy version of this PolSA algorithm. Instead of a hat n plus 1 is the average of a's, but here you have n plus 1. And what we show is that the algorithm, like the parameter estimates obtained from SNR, the stochastic Newton-Raphson algorithm, and the parameter estimates obtained from the PolSA algorithm actually couple at like much faster rate than the actual convergence rate of the parameter sequence. So we show this under like under conditions of a linear model, like you assume that delta n plus 1, the noise sequence is a square integrable martingale difference sequence, and then we assume that A is Hurwitz, and you want to choose zeta so that like I plus zeta A is in the open unit disk. So under these conditions, you can show that the parameter estimates from this and this actually couple with each other. And it also says that the PolSA algorithm has optimal asymptotic variance.
Okay. So the one, basically 1 over n's coverage is much faster than the 1 over square root of n.
So basically what we're doing here is like we're getting rid of this matrix inverse and we're using it in a matrix vector product form, and then we're still getting the optimal asymptotic rate. So any questions?
So computationally, computationally you can just do this.
Yeah.
Just multiplication. No?
Yeah, it's just matrix vector multiplication instead of.
Oh, that's a momentum. Okay. Matrix version of momentum.
Yeah, matrix version of momentum. Exactly.
So a hat n plus 1 would just be A in this case?
Exactly.
Right?
No, I mean, no, so actually it.
I guess what I'm trying to ask it, because it does, delta n plus 1 does not depend on theta. There is no theta term there. Yes, you're just taking.
No, there is a theta term. No, actually, no, I don't think there is. So it's actually something like.
I guess I'm trying to understand. Are you saying that fn plus 1, I should think of fn plus 1 as an plus 1 times theta minus theta star, where an plus 1 is unbiased for A, or
no.
is delta n plus 1?
So I think like fn plus 1 is basically like this, where delta n plus 1 is square integrable martingale difference sequence. I think if you choose fn plus 1 theta to be equal to an plus 1 theta minus bn plus 1, where
but you're only taking derivative for defining a hat n plus 1, right? So everything that's not hitting theta vanishes.
Oh,
so
yeah.
Then it's just a.
So exactly, yeah. So in that case, yes. So if you mean that a hat n plus 1 is converging to a, exactly, that's what it is. But what we do in the algorithm is we sample mean. You take the sample mean of the previous ans.
What is an? In the linear case, no, I'm specifically for the linear model.
Yes.
What is an?
So you have like fn plus 1 is, okay, I didn't write it out here. It's derivative of fn plus 1 at theta.
Right.
It's not a
Which is
function
a.
of theta, but yeah.
Which is a, if fn plus 1 has a form that.
Who's not?
Oh yeah.
No, he's taking, if he takes derivative of that
If this
function,
is the
noise
case.
vanishes. So I think I understand what you're saying, Lynn, but then I would describe it as that there should be an interaction term between the noise and theta.
So
What I'm saying is that there should be some theta in the data.
yeah, I think there is a term theta.
Yeah,
so
that's
exactly.
all I'm saying.
So
That you just, if you give me this formal way of writing, then it would just be.
So yeah, so delta n plus 1 is like, this is a very, so at least in the applications I'm looking at, delta n, so a n plus 1 is going to be like, it's not going to be a, okay? We need to average it out.
But there is still a question that I'm asking there, which is fn plus 1, right? So there are two ways I can think about it. So, okay, f bar is linear. Now, is fn plus 1 also going to be a linear function where the slope has the same mean?
Exactly.
Or is fn plus 1 can be a non-linear zero mean perturbation of a linear function. Which way should I think about it?
So I think for proving this theorem, it might be the case that we assumed it is A, like it's actually the A matrix. But when you look at the, like whatever, for the algorithmic part of it, it's actually A n plus 1. So it's like, the expectation of the linearization is A. The expectation is, the linearization itself is not A. Okay. You had any question? No?
No.
Okay. So, yeah. Now we'll apply all these like new stochastic approximation techniques to actually solve reinforcement learning problems. So, just a one slide overview of the MDP setting which we're looking at. So we'll denote X to be the stationary controlled Markov chain with input sequence U. We'll define PU of X comma A to be the transition probability matrix, meaning given the current state is X and you take an action U, you end up in a state A with PU with probability PU of X comma A. We'll define C to be the cost function and beta to be the discount factor. So what we're interested in is finding this Q function, which is given by this infinite summation over here. Minimum or all input sequence is U, and we know that this Q function solves this Bellman equation. And what we are interested in is doing is like trying to solve this Bellman equation. Okay. So in dynamic programming, the goal is to actually find the Q star that solves the Bellman equation. Say. In Q-learning, what we're interested in doing is like trying to solve an approximation of this. Let's look at a parameterized family of functions Q theta. Theta is an RD. What we are interested in doing is trying to find the theta star that solves this expectation is equal to 0. Now here zeta n can be like a eligibility trace. So there is a general theory called like the Galerkin relaxation of the original problem, which comes from like I think stochastic approximation literature or whatever. And you need to choose this family of functions Q theta and zeta n so that like somehow it gives you intuition of how to say what Q theta star is. Is it very close to Q star or not?
Okay. So for the Q star or Q underbar, what is the Q underbar mean?
I should have been clear. It's basically the minimum or all U prime of Q star. So it's this minimum over here. So this is equal to Q underscore theta star of xn plus 1.
Oh, we have to do the minimum over there.
Yeah. So this is minimum over all U prime Q star of xn plus 1 comma U prime. I should have been careful about that. So yeah.
In Q underbar, have you absorbed the expectation over the minimum, or is it just the minimum?
No, it's just the minimum. So that's the cool thing about this, right? In the Bellman equation, the minimum is inside this expectation here. So what happens here is like if you take this expectation with respect to the steady state distribution of the Markov chain, this one, So it's just xn plus 1 here. So that conditional expectation, given the expectation, disappears. Okay.
Should I be worrying about the specification of the Q theta class?
Yes. So I think like it depends. So I'll get into a little bit of specifics now.
So again, as written, even if I don't have model misspecification, the bottom equation is weaker than the top equation, no? Because the top equation is asking conditionally,
yes,
it always holds.
Yes, this is like solving the Q function exactly. So this, you're not doing that at all. I mean, you may not be doing that.
Yeah.
So
What is the difference?
So first of all, you're looking at a parameterized family Q theta, and if let's say that Q theta star is actually like Q star, even then you're solving this expectation is equal to 0. Okay, and if this expectation holds true for every possible, like, so zeta n is like a d-dimensional vector sequence. Okay, if this expectation holds for every possible vector sequence like zeta n, then you can show that this is equal to that. But in general,
no, but zeta, even for that, zeta n we have to allow zeta n to be a random variable that depends on xn and un.
Yeah, it does. So I should have told. Zeta n is like a random variable that depends on xn. It's fn measurable random variable.
Okay.
Vector, yeah.
So basically, this is zeta n multiplied everything
Inside this, basically, yes. So it's like the projected Bellman equation.
Okay.
So take this and you.
Okay.
Yeah. Okay. So let's look at like slightly more specialized case. Let's look at a linear parameterized family of functions. So Q theta is theta transpose psi. And then the goal is to find theta star so that this is equal to 0. And here, for example, like zeta n could be like the psi of xn un, which is the basis function itself. So that's like the TD0 or algorithm, okay, in TD learning. So how is this connected to stochastic approximation? So this is basic. You can rewrite this equation as f bar of theta star is given by this equation here, a of theta star times theta star minus b, where a of theta star and b are given by this. B is the term which does not depend on theta, and then a of theta. So the thing is, the real issue with Q-learning is that this function a of theta, it has a subtle dependency on the parameter vector theta. If you look at TD learning, you can write it as a theta minus b, but in Q-learning, the A matrix, it depends on the parameter theta through this policy phi theta, and that comes up because of this minimizer over here. Okay, so the phi theta of x is equal to argument u that minimizes q theta of x comma u. So if you basically, like, you can write this q theta star underscore of xn plus 1 as q theta star of xn plus 1 comma phi theta star of xn plus 1, and that's where like this nonlinearity comes in. But consistent with the earlier assumptions, so you can show that in this algorithm, this a of theta is actually a subgradient of this f bar. So if you take the if you evaluate the subgradient of this f bar of theta star, you can show that it's actually a of theta star, which is given by this expectation over here. Okay.
So I am deriving the subgradient of f theta equals a of theta times theta minus b.
F theta times theta minus?
What is the function whose subgradient I am obtaining? It's f of theta equals a theta times theta minus b.
Exactly. That's not true in general, by the way. Only for Q-learning. So in this case, so in general, the subgradient of this is not equal to a of theta. I don't know, but here you need to do like whatever.
So I guess, okay, maybe I'm just, sometimes I'm slow in the mornings, but I don't understand what it, if you give me a general non-convex function, I don't know how to define an object called a subgradient, because subgradient is taking supremum over, a subgradient is basically giving me a lower bound of the function, which is something meaningful in convex functions, because all of those things behave as gradients. But the f of theta here is not convex. So I guess I've never seen people talk about subgradients outside of convex analysis. So I'm just getting tripped up.
Or you just is there some kind of a Jacobian or?
And I need to think a little bit about this. So, but you can show that this a of theta here, it satisfies the subgradient formula. So if this function f bar of theta, so if you take any other function.
So by subgradient, you do mean that it's a valid lower bound.
Exactly, it is a valid lower bound. Yes, you can show that this is a valid lower bound because of it's a very special structure that comes up because of this minimizer over here. So you can show that. Okay. I can show it to you on board or something. Yeah. So in the Watkins Q-learning algorithm, things are a little bit special. So it's basically the root finding problem. Here you let q theta is again a linear parameterized family. You choose this zeta n to be the basis functions itself, psi of x and un. You also choose this basis functions to be the indicator functions, just like in the tabular case. So in this very special setting, you can show that q theta star, when it converges, you can show that it actually is equal to q star. Because of this tabular complete basis case. And you can show that this algorithm converges, but it also has infinite asymptotic variance if you're choosing alpha n is equal to 1 over n. Okay, and that's because the maximum eigenvalue of this A matrix is greater than minus half if beta is bigger than half. You can show that. So yeah.
PolSA max is?
Sorry? Lambda maximum eigenvalue of this matrix A of theta star.
Okay,
it's between minus half and 0.
Oh, okay. Yeah. Okay.
Sorry. Sorry. So first of all the eigenvalues are less than 0, but there's at least one of them which is greater than minus half in this case. So the big question is, can we Zap Q-learning? Can we apply Zap SNR? We can. So this is the simulation of the Zap Q-learning algorithm, and you see that it converges very fast. I'll come back to the results soon. So the tricky thing for us here is not the algorithm itself. So we know how to apply the algorithm. We know what A of theta is. We know how to apply Zap SNR to Q-learning. But the real issue we came across was trying to prove the convergence. So normally how you prove this convergence of a stochastic approximation recursion is you look at the ODE for the parameter sequence. But here we didn't really know how to analyze that ODE. So what we did is we did a transformation of variables using this theory from dynamic programming, which says that if you give me any cost function C, there will be a corresponding Q function which is optimal for that cost function C. And if you give me any Q function, let's say whatever it is, there will be some cost function for which the Q function is optimal for. So there is some sort of a one-to-one mapping between the Q function and the cost function. And what we did was we transformed this variable. So instead of looking at the parameter estimates theta, which correspond to the Q function, we looked at the cost function which corresponds to the...
Only if it is a valid Q function in the sense that it has no Bellman errors.
It has no Bellman errors?
So I don't mean Bellman error in the sense of Bellman optimality equation. I mean, it has no, it makes consistent one-step predictions.
I don't know.
Oh, but no, you're defining the cost function. So could you always engineer this?
You need conditions on this MDP, but it's quite general, I think. You want the solution.
I think you're right.
Yeah. For every cost function, you want the unique solution to be a Q function. So instead of analyzing the ODE for the parameter recursion, what we did was analyze the ODE for the cost function, and we showed that the cost function corresponding to each parameter sequence actually converges to the optimal. So not the optimal, the cost function defined in the problem for the Zap Q-learning algorithm, and this also implies that the algorithm converges, and we also it obviously has optimal variance because it's the Zap SNR algorithm. Okay. So yeah. Any questions? So I'll be moving on to the simulations.
Get a bit lost. So here, I'm wondering that the mixing time of the underlying MDP at all will have an effect to play, right? Because if I think about a pair of states which are very unlikely to transition under my current control.
Definitely, yeah. I mean, so this is all asymptotic. So the ODE analysis is for, yeah.
So do you make the assumption that every state action pair
Definitely.
is infinitely often visible?
Yes. Yeah. Otherwise, I don't think you can prove the convergence of Q-learning algorithm to prove.
This is asymptotic one.
Yes.
You assume you already have stationary. You basically assume that the state transition already mixed.
Yeah. So if so you have a randomized policy. If the randomized policy is such that you visit each and every state action pair is visited infinitely often, then you can do analyze the limit. So this ODE analysis is only for the limiting thing. It does not hold in infinite time. So this is all as n goes to infinity. Okay. So let's look at some of the simulations. So this is comparison of different Q-learning algorithms as a number of iterations of each algorithm. So what I'm plotting here is a maximum Bellman error. I'll evaluate the Bellman error for each and every state action pair. I'm taking the maximum of it. And we see that the Zap Q-learning algorithm converges almost immediately. But these are all the other algorithms, like the Watkins Q-learning algorithm, the speedy Q-learning algorithm, Polyak'smomentum averaging, everything else. It takes a lot of time to converge. And though Polyak'smomentum averaging has optimal asymptotic variance, you still see that it does not converge fast enough. It does not have good transient performance. What happens if you choose gamma n is equal to alpha n? Not only it's theoretically it introduces some sort of a gap, it also does not have very good performance. You can see that here. And you can actually choose alpha n is equal to g of n, with g is equal to this 1500, which again we calculated using this asymptotic variance formula. You see the Lyapunov equation and you try to find the g so that this is the scalar g that kind of minimizes this. And in this case, if you choose g is equal to 1500, you get pretty decent convergence rate. Okay, and so.
Is this where Zap Q is the one you take the inverse one, or?
Yeah, so this is the one wherein we take the inverse.
Okay.
Again, this is also when you take the inverse. This is just a scalar.
Okay.
Okay. And not yet gone into the momentum.
So, in order to run your Zap algorithm, do you need to know the transition matrix in closed form?
No. So that's what. So the thing is, it's the Zap SNR algorithm. So we are trying to estimate the a hat n plus 1 on the go. So you observe a n plus 1, you take the sample average of it, and then you're using that inverse as the matrix gain.
Yeah, so when you so I guess what does it mean to observe a n plus 1 in this specific example of Q-learning? I'm trying
so
to...
it's like, so...
Can we actually go back to the slide where you had... Okay.
Yeah.
Yeah.
So, actually, this is better. This is better.
Like this
so, you observe this. You know this. Without the expectation. And then you take the mean of this.
Okay, so you just need to know the Bellman error.
Yeah, which you need to know the basis functions, and you need to know the policy corresponding to this one. So
you just as long as you have the Bellman error in each state, you okay.
Exactly. Yeah, at each iteration. Yeah.
Okay.
So this is the plot of wherein we're comparing the theoretically calculated asymptotic variance formula with the empirically estimated one. So I estimated the square root of n times the error sequence theta tilde n for multiple values for multiple simulations, and I plotted the histogram over here, and then we see that the theoretically estimated distribution is quite close to the empirically observed for n is equal to 10 power 4, and it's exactly the same for n is equal to 10 power 6. So if you run each algorithm for 10 power 6 iterations, you can see that it's basically the same. Okay, and this is with discount factor beta is equal to 0.99. So here I'm plotting the sorry.
For the previous two sets of plots, what is the kind of MDP that you're doing all these simulations on? Because I'm thinking of just a simple one. Was this the same for the previous plot too?
Yes.
Where Zap is much faster?
Yes. So this is a very simple example. So I should have told this earlier. So you have 6 states. You want to reach goal 6, the goal state 6, starting from any of these initial states, and like the randomized policy I choose is like in any given state you take any action that makes you end up in any of the neighboring states. So the goal is to learn to go to state 6, and you have a cost function associated with transition between each of these states, and you design the reward a cost function so that the reward is highest to reach the goal state 6. It's a very simple MDP problem.
Okay, so the reason I'm getting tripped up is I'm just thinking of a very simple chain-like thing, where somewhere very early on I take some action, and that's basically what gets me it sets the final reward I see. Like imagine I jump off a cliff, right? And after that, only after 100 steps or so, I get the reward for the episode. Yeah. Right, and so feels like no matter how I figure out the step sizes of Q-learning, this should be pretty slow. Any family of Q-learning algorithms should be slow in such a situation, and I can't.
But he's just saying this is the fastest Q-learning algorithm.
Right. So that's why I'm like, so in those situations, it looks like regardless of whether I do Watkins or Zap, they both should have very similar curves.
No, I don't think so. I don't think that is true. Okay. Like I mean, so Watkins will have much slower than I think Zap will. So yeah, it's kind of different things which are affecting the performance. I think here the thing which is affecting is asymptotic variance, which actually I don't know if it has a direct implication from the mixing time of the Markov chain, but maybe. So there's this sigma delta, which is the variance of the zero mean noise sequence, which you can't really change. But given that sigma delta is fixed, you can always like optimize the asymptotic variance. So yeah, you're saying this. I think what you're trying to say is the sigma delta can be like very large. Yeah, there's a problem setting. So here we're comparing the momentum-based algorithms with the Zap Q-learning algorithm, and we see that. So this is basically the same problem earlier, but a much bigger graph. So here the number of state action pairs is 117, and here it's d is equal to 19. And we see that, and this is the online case wherein like you're using a randomized policy to explore, and this is the clock sampling case, basically the synchronous case wherein like you go through each and every state action pair, and then you sample the next state and you update the Q function for that state action pair. And you see that in this case the convergence is like slightly faster, and you see the coupling between like the SNR, the Zap Q-learning algorithm and the PolSA algorithm, and the same over in these two cases. And even the NeSA algorithm, it does quite well, but it is like it's not as good as PolSA, but it has computational complexity which is like much better. Okay. So we also looked at a Q-learning with a function approximation problem. So this is the work by John Tsitsikis and Ben Van Rij. They look at this optimal stopping time in finance problem.
The previous ones were all tabular Q?
Yes. Okay. So this is a function approximation. So we look at a parameterized Q function with linear parameterization, where the parameter is 10-dimensional. The state space is R100, and the Q-learning problem we're looking at, we did an analysis and showed that all the eigenvalues of this A matrix are greater than -half. That means that it definitely has infinite asymptotic variance. But in a different work by Ben Van Rij, they show that like if you use this matrix gain sequence Gn, which they introduce in their paper, you can actually shift the eigenvalues so that the lambda of GA is less than are all smaller than -half. So this was not their motivation to introduce a matrix gain sequence Gn, but it so happened that their matrix gain resulted in this case. But still, this is not good, right? One of the eigenvalues is like very close to -half, and if you remember the plot, the asymptotic variance blows up if eigenvalues is very close to -half. Just by multiplying this matrix gain G with 2 will actually shift the eigenvalues to the maximum eigenvalue to -1, so which will be much better. Which is what we did. We tried to compare like the different Zap Q-learning algorithms along with the GQ-learning algorithms. We're comparing the average rewards over here. We see that for energy, it's a very badly conditioned problem. If you look at this eigenvalues here, so it takes quite a lot of time to actually converge to anything, and we see that the Zap Q-learning algorithms do really well, and the blue GQ algorithm, which is the original algorithm, it does not do great at all. But just by multiplying their gain by 2, it actually does like better than the original algorithm. So we're basically making the asymptotic variance in some sense finite, more finite, I guess. And basically says that the Zap Q-learning algorithm is much better than the GQ learning algorithm. So, so conclusions of future work. So reinforcement learning is not just cursed by dimension, but it also has like serious variance issues. We need better design tools to actually improve the algorithm performance. The asymptotic covariance is an awesome design tool, like as we've seen in this work, and it is also predictive of finite n performance. So for n large as good as like 10 power 4, 10 power 5, we can actually see the CLT behavior, at least in simple problems. But and also this optimal scalar gain G star was again chosen based on asymptotic covariance to minimize asymptotic covariance, and we saw that that is a best scalar gain. And this PolSA and NeSA algorithms, the momentum-based algorithms, proved to be like really good alternatives to the complex SNR algorithm. Okay. Future work, there are a bunch of things which you can extend on top of these things. One of the things which is still open is Q-learning with function approximation. So the ODE analysis we did for the tabular case, I think it can be extended to the general function approximation setting. So I started doing that, but we have some gaps to resolve. But we were able to show it in a, I mean, we have not yet submitted this work, but we are able to show it in a very specialized setting of optimal stopping time problems. And you need like ways to adaptively optimize the algorithm parameters. For example, zeta in the PolSA and NeSA algorithm, and the scalar gain G, and other things. So I think we can borrow tools from the optimization community for this. I think you have a similar situation where you have to find this Lipschitz continuity coefficient and mu convexity coefficient on the go. Right? So further reduction in variance is possible using control variates. So this is like I think it's a very, very powerful technique to actually reduce the variance even further, and it's like it's kind of complementary to whatever I showed here. So that's good. Applications of all these algorithms, stochastic optimization. So I spoke about the general root finding problem, but I don't know if it's already like kind of related topics are already existing in stochastic optimization or not, and maybe we can extend this to stochastic optimization. Okay, thank you. And yeah, so here are some references. Like this is the last year the Zap Q-learning paper, and this is the extended version on archive. And this is this, we just put it up on archive, the momentum-based methods. And my advisor also, Shani, also gave a like 2 hours tutorial on in Simons. So this is the links. And this is like some of my other work. So I also worked on something that is differential Td learning. So wherein instead of trying to find the zero of the Bellman equation, you try to find the zero of the gradient of the Bellman equation with respect to the state. So and for that we needed some more assumptions on this ergodicity of Markov chains and other things. So anyway, and there are a lot of references in there. Thank you. Yeah.
Like with control variates, does the asymptotic variance change?
No. So I should
for a finite sample, like in practice, you want to see better work.
Yes. So that's what and it's pretty common, I think. Like people have used that in reinforcement learning, actor-critic methods and other things.
But could we justify their use through an argument that's not empirical but actually theoretical? Because asymptotic variance wouldn't tell us that.
Yeah, that's what I don't know. I think it's possible. Like maybe it tells us using asymptotic form. Maybe we can use this analysis techniques to actually. I'm just thinking that if we have an additional term inside this stochastic approximation thing, how it will actually affect the stochastic approximation recursion I had earlier. And maybe it is possible to analyze that theoretically, yes. Like any of these algorithms. It's very similar to all this SVRG, Saga and other things, except that instead of like, there's no batch here, like everything is online. So you can maybe estimate it online, like the means. So maybe like a 3 time scale stochastic approximation algorithm wherein you estimate like 3 parallel things, control variates and maybe.
I mean, if somebody gave you the control variate rather than you having to estimate it, then it will affect your asymptotic, right? That's a way of showing where they can be useful, which is kind of how we partly show it, for instance, with W robust type variance, right?
Thanks, Aditya.